Okay, so this is what we discussed last week, that you have error signal, which is what we call tracking error. And tracking error is the difference between the input and the output. And the difference between the input and the output, basically input is the desired output and output is the actual output. So the difference between the two is the tracking error. And that tracking error, we need to minimize the tracking error in order to achieve the output, which is our desired output. Now, in this case, of course, we have our desired output, which is our input RS. We have the external disturbance TDS, and then we have the internal error signal, internal noise signal, which is NS. And we look at the output expression in the presence of all three input signals, RS, TDS, and NS. And with RS and TDS, we did the derivation in the last chapter, as if you have those two signals, what will be the output expression? We did not do it with NS, but you can do the same way like we did for RS and TDS using superposition. But we did analyze the error signal, and expression of error signal, as you can see, is that we defined a gain loop, which is the product of the controller gain and the process gain, GCS times GS. And then we defined the error signal in terms of the loop gain and the process gain. GS is the process gain and LS is the loop gain, which is the product of the process gain and the controller gain. We also define what is the sensitivity of the system, that is how sensitive it is with respect to the changes in some parameter in the system. And right now I just showed you the expression that sensitivity is defined in terms of the loop gain as 1 over 1 plus LS. We're gonna confirm this expression today as why sensitivity is defined by this expression, 1 over 1 plus LS, which is 1 over 1 plus the product of controller gain and the process gain. And then we also define the complementary sensitivity in terms of the loop gain. And if we add the sensitivity and complementary sensitivity, our result is one, that is, if sensitivity is increasing, complementary sensitivity is going to be decreasing, as we can see from equation 4.7. Then we moved on to discuss what should we change in order to reduce the effect of the disturbance signal and the noise signal on the error. And it turned out that, from our discussion, it turned out that to reduce the effect of disturbance on the tracking error, our loop gain need to be large over the frequencies of disturbance, which are lower band of frequencies. And to increase the value of LS, we have to increase the controller gain. Again, coming from the expression from the last slide. Also, to reduce the effect of the measurement noise, internal noise, we have to reduce the value of the loop gain or reduce the value of the controller gain. Of course, we cannot do that at the same time, but we know that our disturbance signal is at low frequencies, and our noise signal generally is at high frequencies. So at low frequencies, we have to increase the gain of the controller, and high frequency, we have to decrease the gain of controller. And that's how we came up with that we require the controller gain, GC transfer function, to reflect some sort of low pass type of system. So when you are creating GCS, the controller gain, and you're creating the expression of the controller gain, you know, S square plus this over S cube plus whatever, that expression, when you analyze in terms of frequency, that expression should show you a low pass filter characteristics. And if you have that, then you can reject the disturbance over low frequencies, and you can reject the noise at high frequencies, because your gain is high at low frequencies and your gain is low, the controller gain at low frequencies. So that was the conclusion of the analysis of this equation, the equation for the tracking error. Now let's look at the sensitivity of the system as what exactly is sensitivity of the system. Sensitivity of a control system we define as the ratio of the percentage change in the system's transfer function to the percentage change of the process transfer function. So that is how mathematically sensitivity is defined. So you can see that expression. This is given in terms of course, delta function, but it's also derivative is also given. So rate of change, ratio of the percentage change in the system's transfer function. So percentage change in the system's transfer function is in the numerator, that is derivative of Ts with respect to Ts, or delta Ts over Ts. This is, of course, if the change is large, and this is if the change is small. And it shows partial derivative instead of regular derivative, because transfer function is a function of many variables. It's not just divided by the rate of change of the process gain, process transfer function with respect to the transfer function. So this is how you're defining your sensitivity. In other words, we can also write sensitivity as right. This is a common expression that we use for the sensitivity. Rate of change of transfer function with respect to the process times the ratio between the process gain and the transfer function. So that's the same expression written in that. And here you can see derivative of natural log of t times derivative of natural log of g, which comes out to be the same as this. Derivative of natural log of t is 1 over t times derivative of t, and derivative of natural log of g is 1 over g times derivative of g. So it's the same thing as this. Transfer function, if it's a unity feedback system, this is for the unity feedback system, can be given by GCS GS over 1 plus GCS GS. And this is only with EDS and NS to be equal to 0. Only RS is present in the circuit, in the system. So the transfer function of a unity feedback system with no noise, external or internal, is given by this expression as we have discussed before. From this, if TDS is 0 and NS is 0, then the transfer function is going to be given by 1 plus GCS GS over 1 plus GCS GS, assuming that it's a unity feedback system. And we did the derivation of that as well quite a few times. So if we take that transfer function for the unity feedback system and we apply this, then we are going to get this expression. Now, how are we going to get this expression? We can apply it real quick and then I can show you. Let's see. Let me insert a slide. So let's see how we're going to get the sensitivity of this, the transfer function with respect to the process as this expression. So our transfer function is GCS GS over 1 plus GCS GS. Again, for this, HS is 1 and TDS is 0 and NS is 0. So only RS is active, right? if we calculate the sensitivity of the transfer function with respect to the process gain, GS, and that's why we're taking partial derivative, because transfer function is also a function of GCS. So it's not just a function of GS. That's why we're taking partial derivative with respect to only GS. So if we take, and transfer sensitivity is given by whatever sensitivity you are taking for the item, which is in this case the transfer function, with respect to the item, which is your process gain. This is how it is written, as you can see on the previous slide. Sensitivity of T with respect to G. And this is given by derivative of the transfer function with respect to the process gain times the process gain over the transfer function. So if we take the derivative, and this is your transfer function, we take the derivative with respect to only G. So we will assume GCS is constant right now. We are taking only with respect to GS. So if we apply the derivative property of division, how are we going to do that? dt over dg. If you apply the derivative property with the division u over v, so anybody remember? Okay, so u times derivative of v minus v times derivative of u, right? Or opposite of that. Okay, so now numerator is GCS GS. So let's go with that. GCS GS and the derivative of the denominator. Derivative of the denominator, remember, we are taking derivative with respect to GS. So GCS is considered to be constant. So that's going to be GCS. Just make sure that I'm doing it correctly. It's not opposite of that. I thought it was V du over dt. Yeah, that's what I was thinking. It's derivative of the numerator minus. Okay, so let's go back. So derivative of the, so let me write this down. Derivative of the numerator, which is derivative of GCS GS times the denominator, which is 1 plus GCS GS minus derivative of the denominator times numerator. Okay, so GCS GS times the derivative of denominator, which is 1 plus GCG. So that is the numerator, and the denominator is the square of V. So 1 plus GCS GS squares. And then of course you have times G over T. So I'm going to write this here since I don't have room over there. I'm going to write this G over T here. So again, we are using derivative, the division property of derivative of the numerator times denominator minus derivative of the denominator times numerator divided by denominator square. So let's see what we cancel out. So derivative of GCS GS, I remember we are taking with respect to GS, with respect to GS, with respect to GS. That's going to give us GCS. So GCS times 1 plus GCS GS. 1 plus GCS GS. And then the second term is going to be minus GCS GS times the derivative of this, which is again going to be GCS divided by 1 plus GCS GS square times G over T. So G is GCS and T is GCS GS over 1 plus GCS. Now a bunch of stuff is going to cancel out, so don't worry about it. So here you have, let's see, what do we have? GCS. So let me cancel this out first. GCS and this GCS and this GCS cancel out. So that's going to be 1 plus GCS GS over GS. So that's going to GCS plus GCS square, this GCS times GCS times GS minus GCS square times GS over 1 plus GCS GS square times 1 plus GCS GS is going to go in the denominator, in the numerator, and this divided by GS. So this is cancelled out by 1 power, this is cancelled out, and then GCS is cancelled out as well. GCS is the only thing that will be left after you cancel this out, is going to be 0. So now we can cancel GCS out. So the only thing that is left here is 1 over 1 plus GCS GS. Insert another slide. Insert another slide. Let's just write down here maybe. So let me write down sensitivity of T with respect to G. So that's how we got sensitivity 1 over GCS GS, which is right here, 1 over GCS GS. And again, if we go back and show you that we took the sensitivity right here, sensitivity of the system 1 over 1 plus LS, which is 1 over GCS, 1 plus GCS GS. So although here we did not do any derivation, we just defined that the sensitivity of the system is defined by that equation. But as you can see, after we did the derivation, it came out to be the same expression, 1 over 1 plus GCS GS. So sensitivity of the system with respect to the changes in the process. This is how we read it. Sensitivity of the transfer function with respect to changes in the process is given by 1 over 1 plus the loop gain, and the loop gain is GCS times GS. And if you are trying to figure out the sensitivity with any variable alpha of the process, then we can apply the chain rule. As you can see, sensitivity of the transfer function with respect to alpha is equal to sensitivity of the transfer function with respect to G and sensitivity of G with respect to alpha. So we can apply chain rule to get that, although you can apply directly sensitivity of transfer function with respect to alpha, and you can write this down as derivative of transfer function with respect to alpha times alpha over T. So you can directly calculate the sensitivity with a change in variable of alpha as well, instead of applying the chain rule, but you can also apply the chain. If a system is too sensitive with the changes of a parameter, then you have to be careful when you're designing it. Our goal is that system should not be very sensitive. The transfer function should not be very sensitive with a specific parameter of the process. All right, let's see, we have a problem. Block diagram of a closed loop system is given to you. This system is used to track the sun to obtain maximum power from a photovoltaic array. A transfer function is not given to you. I'm going to show you the transfer function. I forgot to put the transfer function here. So let's put the transfer function first. The transfer function of this system is given by, of course, GS over 1 plus GS. And let's see, this is GS is given by 100 over tau S plus 1. So GS is 100 over tau S plus 1. Tau is, assume tau is 3 seconds. Determine sensitivity of the system with the small changes in the time. Tau is a time constant, in the small changes of the time constant. And then time constant of the complete system, closed loop system. Tau is a time constant of only the process GS. And we have to figure out what is the time constant of the complete transfer function response. All right, first thing, since we are calculating sensitivity and we know how to calculate sensitivity, the first thing that we need to know is to define what is the transfer function in terms of tau. So let's write down the transfer function in terms of tau. Simplify it. Tau is plus 1 plus 100. So that's going to be 100 over tau is plus 101. Tau s plus 101. And then to get rid of any coefficient associated with s in the denominator, we can divide the numerator and denominator by tau. And we can write down 100 over tau over s plus 101 over tau. And remember, tau is 3 seconds given to us, so we can always go ahead and put tau is equal to 3 seconds. All right, so let me ask you this first question. Let's answer the second part first. The time constant of the closed loop response. What do you think is the time constant of the closed loop response from the transfer function? But that's the transfer function of the closed loop response, the complete system. What is the time constant from this expression? It's not 1 over tau, but it comes from that that figure, of course. So if you're putting this in the time response, time domain, and you're taking the inverse Laplace, what will be your result of inverse Laplace? Yeah. So 100 over tau is constant, and what did you say next? E to the power negative 101 over tau times t, right? So if you write that down, e to the power negative 101 over tau times t, from this, what will be your time constant? E to the, I can write this down as e to the power, remember this is alpha, right? This is your alpha. So t over 1 over alpha. You can write this down as e to the power negative t divided by tau over 101. And that's the time constant of your system. Remember, what is the definition of time constant? the time it takes for the system to drop down to 36% of its peak value, right? That's a time constant. So when the time becomes equal to whatever you have in the denominator, it's going to have e to the power -1. And e to the power -1 is, of course, 36% or 0.36. So when you have alpha or sigma or whatever variable you are taking, e to the power -sigma t or st, whatever, then 1 over this is the time constant, remember. That's, again, that's the concept of the, remember the dominant root that we discussed. If s is closer to your origin, that is going to take longer for the exponential function to die down. Why? Because the closer it is, 1 over that value is going to be larger. If that thing is farther away from the origin, let's say s is equal to -100. So 1 over 100 is 0.01. E to the power -t over 0.01 is going to take only 0.01 second for the response to drop down to 36% of the peak value. But if you have s is equal to -2, then -t over 2, which is 1 over 2 is 0.5. So -t over 0.5 is going to take half a second for the response to drop down. So the closer the s value is to the origin, the time constant is going to be larger because the time constant is 1 over that value, right? So anytime it is given to you s plus a, right? S plus a in the time domain is e to the power -at. The time constant for that is 1 over a, right? You can write down as 1 over a. I'm showing you alpha, but this is a, so 1 over a. That's the time constant of the system. So in this case, the time constant of the system is 3 over, tau is 3 given, so 3 over 101. That's the time constant for the second part that you see. So let's write down that first. So B part, time constant of the system is, let's write down tau sys to differentiate it from tau. Tau system is 1 tau over 101 or 3 over 101. So any question about this? Make sure you understand this concept. That's something that you'll be using very frequently. So let me use lighter color. This is the constant system. It's going to take 3 over 101 seconds for the system response to drop down to 36% of its peak value. The peak value, of course, is 100 over tau, 100 over 3. So 33.3 is the peak value of the system. And based on the, again, based on what input you're using, if you're using step input. So anyway, so that's the second part. This is the time constant of the system. And the first part is, what was the first part? Oh, sensitivity of the system. So let's calculate the sensitivity of the system. Sensitivity of the system with the changes in the time constant of the process, which is tau. S of transfer function with the changes in tau. So instead of using chain rule, I'm just going to apply dt over d tau times tau over. All right, dt over d tau, again, we're going to use, so remember our t is, transfer function is 100, what is that, 100 over tau divided by s plus 101 over tau. This is our transfer function. So rate of change of the transfer function with respect to the changes in tau. Again, we're going to use uv. So derivative of the numerator times the denominator. So s plus 101 over tau, and derivative of the numerator with respect to tau is going to be d over d tau 100 over minus derivative of the denominator with respect to tau, s plus 101 over tau, times the numerator 100 divided by s plus 101 over tau square times tau over t, and t is 100 over tau. So this is the expansion of the sensitivity expression. Yes. Could be, you may be right. Let's see. 100 over tau is plus 1. Yeah, it's easier. You're right. So let's take that. 100 over. I can write on the other. As tau t is equal to, so this is tau s plus 101. So 100 over tau s plus 101. So yeah, you're right. It might be easier to take the derivative of that. So let's write that down real quick. Denominator is tau s plus 1. And the numerator is simply a constant, so that's going to turn out to be 0 minus derivative of the denominator tau s plus 1 times the numerator, which is 100, divided by tau s plus 101 square over tau over. So derivative of constant is going to be 0. So this whole term is going to become 0. And we have a derivative of tau s plus 1, that's going to be s. So negative 100 times s over tau s plus 101 square times. All right, we have tau times tau s plus 1, 101 divided by 100. So again, we cancel out this 100. We cancel out tau s 101 with 1. So our final result came out to be negative tau s over tau s plus 101. And now we can divide by tau negative s over s plus 101 over. So that's the sensitivity expression for the transfer function with respect to the changes in the value of the time constant of the process gain. And of course, S is, remember, frequency. So at different frequencies, when you put different frequencies, you can find at what frequency the sensitivity of the system, again, with respect to the changes in the value of tau, is what. S is the frequency domain, remember, complex frequency. All right, guys. Let's go ahead and take a 10-minute break and then start back around 10:30. So the next topic, we're going to look at disturbance signals in feedback system, something that we already discussed actually earlier in this chapter, as at what frequencies we can eliminate or reduce rather the disturbance signals and the noise signal. So same discussion is carried out in this topic. That feedback system, of course, they partially eliminates or at least reduce the effect of disturbance signal. Disturbance signal can be any unwanted signal, whether externally or internally to the system. And we discussed that the loop gain must be large at the frequencies where the external disturbance signals are pronounced. That is at low frequencies, so that we can remove the effect of the external disturbance. So error signal only because of the disturbance signal can be given by that expression, negative SSGS TDS. That expression is coming from previously slide number 4. So if we only want to look at the error signal due to the disturbance signal, it is keeping RS and NS to be 0. It is GS over 1 plus GCS GS. And 1 plus GCS GS is, of course, the loop gain. So the discussion over here is, if you want to reduce the disturbance signal, if you want to reduce the error due to the disturbance signal, then the denominator has to be large. That is, the value of the loop gain must be large. And loop gain, remember, is the product of the controller gain times the process gain. So loop gain is the product of the controller gain and the process gain. In other words, your controller gain must be large in order to reduce the effect of the disturbance on the error, or in order to reduce the error due to disturbance, in other words. And those are at low frequencies, because disturbance signals are mostly at low frequencies. So the sensitivity, because this is also the sensitivity, 1 over GCS GS, sensitivity of the expression is 1 over GCS GS, 1 plus, or 1 over 1 plus LS. So the sensitivity function must be small over the range of the frequencies over which disturbance signal need to be reduced. Sensitivity is this right here. To reduce the sensitivity, of course, the controller gain needs to be large. If you look at the measurement noise and how it affects the error, then we keep input signal and external disturbance to be 0, and the error due to just noise is going to be sensitivity over 1 plus, loop gain over 1 plus loop gain. So the error signal only because of the noise is loop gain over 1 plus loop gain, which is the complementary sensitivity signal. So the loop gain must be smaller, which in turn means the complementary sensitivity function must be smaller, as shown here, in order to reduce the error due to only the noise. So once again, comes down to the same thing, that the loop gain has to be large at the frequencies where you want to reduce the effect of the external disturbance Td, and loop gain has to be small over which you want to reduce the effect of internal noise Ns. So again, it comes down to frequencies. At what frequencies you want to make the loop gain to be smaller, and at what frequencies you want to make the loop gain to be larger. And again, at low frequencies where the external noise is more pronounced, you want to make the loop gain to be larger. And at high frequencies where the internal noise is more pronounced, you want to make the loop gain to be smaller. And again, loop gain goes back to the gain of the controller, GCS. So you want to make the controller gain to be larger at low frequencies and smaller at high frequencies. So we discussed that already. Since the loop gain is the product of controller gain and process gain for a given process, the designer must design the controller to have large gain at lower frequencies to reject external disturbance, and low gain at high frequency to reject measurement noise. Let's look at the second example. A digital audio system is designed to maximize the effect of disturbance or minimize the effect of disturbances as shown in this figure. As an approximation, we may represent GS is equal to K2. So this GS is a gain K2. Calculate the sensitivity of the system due to the changes in the gain K2. That's the first part. Calculate the effect of the disturbance noise Td on the output voltage. And what value would you select for the amplifier gain K? Amplifier gain should be K1. Amplifier gain K1 to minimize the effect of the disturbance. So let's do it one by one, starting with A. What should be the process gain K2? Or what should be the effect of the process gain K2 on the sensitivity of the system? So sensitivity of the system, transfer function with respect to K2, which is the rate of change of the transfer function with respect to the changes in K2 times K2 over transfer function. So first we're going to write down the transfer function of the system. Let's do that. I want to write down right over here. Do this. Move it up a little bit. Let's figure it up. And I'm going to write down transfer function right at the bottom. Okay, so the transfer function. Who's going to tell me what will be the expression of the transfer function for this one? Again, assuming that this is our, and we're going to keep, initially we're going to keep the TDS to be equal to 0. Yes, what will be the transfer function? V out over V in, keeping TDS to be 0. Okay, K1, K2 over 1 plus K1, K2. And disturbance, we are not assuming right now. So when you take the sensitivity with respect to K2 for this transfer function, it's pretty straightforward. You have derivative of the numerator, which will be K1 times denominator 1 plus K1, K2 minus derivative of the denominator, which is again K1 times the numerator K1, K2 divided by 1 plus K1, K2 square times K2 over K1, K2 over K2, K2 cancelled out. This will be cancelled out by 1 power when we take this in the numerator. sensitivity of the transfer function with respect to K2 is going to be K1 plus K1 square K2 minus K1 square K2, so that those two terms will be cancelled out as well. And we're going to have simply K1 in the numerator plus 1 over K1 K2 times 1 over K1. So that will also cancel out K1 and K. So transfer function simply, your sensitivity will simply be 1 over K1 K2, which means to reduce the effect of the process gain K2 on the sensitivity of the system, we need to have that sensitivity value to be large. What value? That of course have to be decided, but in order to reduce the effect of K2 on the transfer function, K2 has to be a little large value. Yes, go ahead. So sensitivity is going to be based upon specific inputs. So right now you are looking at only one input, which is the actual RS input, right? If you want only the TDS in the system, then you're gonna first write down the transfer function of that, and then you're gonna find out how the sensitivity is going to deal with that. Calculate the effect of disturbance noise TDS on V naught. So let's look at, first we're gonna look at what will be the expression of V naught in terms of TDS, and that will give us what effect of TDS is on V naught and what parameter should we change in order to reduce that effect on TD naught. So let's look at that second part. Okay, so now we're gonna keep RS to be 0. 0 to find the effect of TDS on the output voltage. RS in this case is V input basically. V input S is to be 0. V input and V out. Okay, so if we keep, let's write this down here. Let's go back to this figure. If we keep V input S to be 0 and want to write down the output expression in terms of the disturbance, how are we going to do that? Who's going to tell me? Again, you're going to go and follow each signal. So here, what will be your signal? Say negative V output S. All right, and then you're going to have multiplied by the gain of the controller, K1, negative K1 V output. That's going to be added into the disturbance. So TD minus K1 V out. And finally, the whole thing is, it goes through the process multiplied by the process gain. So the output is going to be K2 times TD minus K1. So that's going to be your V out. Assuming V input to be 0, remember. So let's write that expression down. V out is equal to K2 TD minus K1 V out. V out S is equal to K2 TDS minus K1 V out. So since we are trying to figure out what is V out in terms of KT, so V out on one side of the equation, V out 1 plus K1 K2 is equal to K2 times TDS. So this is the output voltage for because of your disturbance. K2 is the process gain, K1 is the controller gain. So if your process gain is kept constant, K2 is not changing, let's say, then of course K1 has to be quite large in order to reduce the output value because of the disturbance. In order to reject any disturbance. And that's part C actually, but not what it. What this is what value would you select for K1 to minimize the effect of disturbance. So that's part C. Any question, guys, about this? Now, what exact values are we going to take? There's an example that we're going to discuss towards the end, where we're going to take a specific values of gain, and then we will see how those specific values are going to affect the disturbance on the output as well as the actual value of the output. Actual value based on the input value. That's the last example in this chapter. Control of the transient response. Again, feedback signal, you can control how the transient response should look like. Transient response, of course, we all know that the response that is changing with respect to time, a steady state is the value that is not changing with respect to time. Transient response is supposed to be adjusted for control systems such that the desired response of the system is achieved based upon how long you want the transient response to last, or the tracking error is within the limits. Now, I'm not going to go over this example because I have already solved this example here. So we have a system, industrial motor speed control system, given by a bunch of BJTs, and you have diodes and a motor, power supply, tachometer, variable resistor, so on and so forth. And the block diagram of the system is shown here. Input is taken as K2 E over S as a step input. And you have the amplifier controller, basically, amplifier gain Ka, motor transfer function Gs, and tachometer gains, I believe, is Kt. The output is speed is omega S, and tachometer is going to convert the speed into the voltage, which will be compared against the input voltage to produce a gain, and that gain is going to control the gain of the amplifier. So this thing is solved here. We calculated the transfer function first, and then gain of the transfer function of the motor GS may be given by its gain K1 and equivalent time constant T1 as follows. So we assume that the gain of the transfer function can be given by an expression that has a gain of the transfer function K1 and the time constant to be tau 1. And we plug in that value of GS in this expression to get the transfer function of the system. The amplifier gain or the tachometer gain can be changed to acquire the required transient response. For the step input as shown, the speed response can be determined as follows. So we went ahead and we plug in right over here. We divided both sides of the equation by tau 1 over here. And this is the expression that we came out to be. Then we plug in the value of RS here, and then solved it and basically wrote down the Laplace response, and then took the inverse Laplace transform to write down the time domain response. And it has a bunch of variables that you can see. It has a variable of the amplifier gain, it has a variable of the process gain, and the tachometer gain, and so on and so forth. The time constant right over here. Time constant is 1 over this term, of course. That's going to be the time constant of the whole system. And then we went ahead and we plotted the response of the system, the closed loop response, and the open loop response. And we observed that it can reach to its final speed very quickly if we adjust the parameters such that the transient response can become quite small. So this is the transient response until it hit your final speed in seconds. And in this case, you can see then the open loop system response, if there is no feedback, there is no tachometer, then the open loop system response is going to take very long before it reaches to the speed, but we can adjust the transient response of the closed loop system such that the final value can be achieved much quicker. So go over this example. Of course, as I said, there are a lot of variables, math involved. If I read those things, it's not going to make much sense, but when you do it, that's going to make much more sense to you. The steady state value of the error. In general, we need it to be 0, the steady state value of the error. Many times it is not 0. Our goal is to make it as small as possible. That is, the output must be very close to the input. In addition to adjusting the transient response and system being less sensitive to the parameter changes due to disturbance, closed loop system may also have significantly small steady state error as compared to the open loop system. One of the examples, of course, as you can see in the previous slide, that this speed is a steady state at 1. If your input is a step response, then the output is also a step response. And this, I don't know how long it's going to take, but it may or may not hit this value. So there may be some difference between the steady state value and the final value of the open loop system. And that difference is the error between the desired output and the actual output. So we can adjust the parameter, of course, to reduce that difference in the feedback system, but we cannot do that in the open loop system. Tracking error on a unity feedback system, if we assume all the disturbance to be 0, then we can write down the tracking error expression by this expression. And again, we did that. It's coming from right over here. ES is equal to 1 over 1 plus GCS times RS. That's the tracking error only because of RS. If we assume TDS and NS to be 0. If we assume that our input is a step, and if we use the final value theorem, then S and S will be cancelled out, and your steady state error is going to be 1 over 1 plus GCS GS when S tends to 0, or in other words, 1 over 1 plus the value of the controller gain at 0, S is equal to 0, and the value of the process gain at S is equal to 0. Or in other words, the value of the loop gain, 1 over 1 plus the value of the loop gain to be at 0. So the DC loop gain, remember S is equal to 0 mean that frequency is 0, S is frequency. S is equal to 0 mean frequency is 0, that is, you have the DC value at S is equal to 0. So the DC loop gain L0 can be made significantly large in order to minimize the steady state error, such that the output response and the desired response may be very close to each other. All right, example. A robotic arm and a camera can be used to pick fruits as shown in this figure. The camera is used to close the feedback loop to a microcomputer, which controls the arm of the transfer, the arm. There should be a period over here. The transfer function of the process can be given by GCS is equal to K over S plus 5 square. Calculate the expected steady state error of the gripper for a step command A as a function of K, and K in this case is the DC value for the process gain. All right, so let's look at, in this case, my input signal RS, this is my desired input signal. In this case, my input signal is A times UT, or RS is equal to A over S, because my input is a step command as it is given to us. The transfer function of the system is simply GS over 1 plus GS. Process is GS, unity feedback system, and GS is K over S plus 5 square. So K over S plus 5 square divided by S plus 5 square plus K. This is after simplification. All right, what is the error? Tracking error. Because to find a steady state error, we will write down the equation for the tracking error, and then we will see what is the steady state error. So the tracking error, ES as we define it, is the difference between the output and the input, or the input and the output, sorry. And output is transfer function times input. So the tracking error can also be written as 1 minus TS times RS. And if we want to find, remember, we have to find what? We have to find the expected steady state error of the gripper for a step command. We already applied the step command A over S. So we have to look at what is the expected steady state error for the step command. So to find the steady state error, we can apply the final value theorem. Final value theorem to find the steady state error. E steady state is equal to limit s tends to 0, s times es, limit s tends to 0, es is 1 minus transfer function times input, and we know that the input is a over s. So this s will be cancelled out, and we apply the limit. E steady state will be equal to a times 1 minus the value of the transfer function at dc, that is 0. When we plug in, s is equal to 0. So let's go ahead and look at what is the value of transfer function at dc. When we put s is equal to 0, we're going to have k, s will be 0, this s will be 0, so k over 25 plus k. A 1 minus k over 25. 25 plus k minus k is 25 over. And that is the steady state error for a step input in terms of k. K is what? K is the gain of the GS at DC. Oh no, actually gain of GC is k over 25. K is part of the gain basically. Again, k has to be quite large in this case in order for the steady state error to become close to 0. That is, the output and input becomes quite close to each other. Any question so far? Yeah. Go ahead. Oh, this, so GS is going to be k over s plus 5 square, and then it's going to be 1 plus k over s plus 5 square. So when I simplify that, that's going to be s plus 5 square plus k, and then s plus 5 square in the numerator and s plus 5 square in the denominator, they will be cancelled out. Yeah. Okay, let's look at what we know, that the feedback control systems are better systems because they can reduce the effect of disturbance, noise. You can control the parameters of the controller such that your transient response can be adjusted as well as your steady state error can become close to zero. But what is the cost that you have to pay in order to create the closed loop systems over the open loop systems? So when you add a feedback to control system, of course, you have advantages as we discussed, a lot of advantages. Reducing error if the output is changed due to change in the system parameter because of disturbance. However, we have to have some cost in order to have those extra advantages. Of course, you have increased number of components. Your system is more complex. Loss of gain as compared to an open loop system. Open loop gain is going to be GCS-GS. So if you have just open loop system and you have GCS and GS and the output, then of course the transfer function is going to be simply product of GCS-GS. But if you have a closed loop system, then assuming feedback is 1, then what's going to happen? Your overall gain is reduced. So for the closed loop system, of course, your gain is GCS-GS over 1 plus GCS-GS. So the denominator 1 plus GCS-GS is going to reduce the overall gain of the system at DC as well as other frequencies. That's one disadvantage, not a big disadvantage, but still. Open loop systems are always stable, whereas closed loop system may become unstable. That's perhaps one of the biggest disadvantage. That when you're designing as an engineer, when you're designing closed loop system, and we're going to discuss the stability of the systems, if you're designing an open loop system, it can never become unstable, and you will see why. But if you're designing closed loop system, then your system can become unstable, they can be marginally stable, or they can be stable. You have 3 types of stability associated with closed loop systems. Either it will be marginally stable, that is, marginally stable systems are that the system may become stable or unstable based on what type of input you're using. And again, that discussion is in the future. A stable system, for any stable input, the output will always be stable. An unstable system, even if your system is stable, the output is going to become unstable. Of course, if your input is unstable, then your output will be unstable, irrespective if your system is stable or unstable. So we don't give unstable input. Unstable input means what? If your input is increasing with respect to time, that's an unstable input, basically, like a linear input. So you're not controlling that input. You just let it increase with respect to time. Of course, the output is also going to increase with respect to time and becomes unstable eventually. So our input has to be stable, of course, in order for the output to be stable. What are stable inputs? Your DC value is a stable input. Sinusoidal value is a stable input. Exponentially decreasing value is stable input. But anytime you have exponentially increasing value or a linear value or a second order polynomial, and you're not controlling that, then those outputs are considered to be unstable. Those inputs are considered to be unstable inputs. So 3 points are given here. And these 3 points basically are disadvantages of closed loop system. But the advantages of the feedback system basically outweighs its disadvantages. So most of the systems, that's why practical systems, they are closed loop system. Most of the systems that you create for your senior design, they're always closed loop system. Most of the time when you're using in your senior design, you're getting values from sensors and stuff, comparing values against your conditions that are here in your program. If the values are higher or lower, you're trying to adjust that, or you're trying to adjust the maneuver of whatever you're, if you're a robot or something. So most of your system are closed loop systems, basically. All right, the last example in this chapter, I partially solved it. One part I solved it because it required MATLAB and all those things that I put in there. But then we're going to solve a few parts of this problem. So this problem is from the book, one of the examples in the book, English Channel boring machine. The construction of the tunnel under the English Channel from France to Great Britain began in December 1987. First connection of the boring tunnel from each country was achieved in 1990. The tunnel is 23.5 miles long and it's bored 200 feet below sea level. The tunnel completed 1992. Total cost was 14 billion, if I remember correctly. It's not $14, of course. It has to be 14 billion. Oh, the next slide is billion. Okay, I thought it's. All right. Accommodates 50 train trips daily. The construction is critical link between Europe and Great Britain, making it possible for the train to travel from London to Paris in only 3 hours. The machines operating from each side bored towards the middle. To link up accurately in the middle of the channel, laser guidance system kept the machines precisely aligned. A model of the boring machine is given in that block diagram. YS is the actual angle of the direction of travel of the boring machine, and RS is the desired angle. The effect of load on the machine is represented. Let me move this down. This is the effect of the load on the machine is represented by the disturbance TDS. So you have the controller, GCS, the transfer function of the controller is given to you, K plus 11S. System is the boring machine, and the transfer function of the boring machine is given to you, 1 over S times S plus 1. And RS is the desired angle at which it has to travel, and YS is the actual angle. So what we are doing with this problem, select the value of K so that the response to the input angle changes is desirable while we maintain minimal error due to the disturbance. Okay. So first, we are going to write down the expression of the system or output, expression of the output YS in terms of both inputs, RS and TDS. And then we will see for which input we want to figure out the effect or whatever it is being asked in the problem. So we're going to write down in terms of both RS and TDS. So we're going to apply again superposition like we did before. And let's say let TDS is equal to 0. And YS, let's call it Y1S due to RS. Y1S will simply be GCS GS over 1 plus GCS GS times RS. K plus 11S, 1 over S times S plus 1. One over S times S plus 1. right? We'll simplify this. SS plus 1 will be cancelled out, and we are going to get k plus 11s over s square plus s plus k plus 11s or s, or ys will be equal to k plus 11s over s square, s plus 11s 12s, 12s plus k times r. So that's the output only because of the input rs. And now we're going to find the output because of the disturbance signal, and then write down the one expression that has both input signal and the disturbance. All right, before we move on, let's write down what is the error. Oh, actually, we're going to come back to that later. All right, next, let me go to the next slide then. Now let our s is equal to 0 and write down y due to TDS. And let's call this y2s. All right, due to TDS, we already did that several times when RS is kept 0. I'm not going to do that again. Let's go back and see where we did that. It's going to be, did that some recently, we did it somewhere right here. Yeah, right here. Okay. So that is going to be ys is equal to gs times TDS minus GCS times the output. Or using this equation, K2 was GS and K1 is GCS. So GS over 1 plus GCS GS times TDS. So we just did that. That's why I'm not doing it again. I'm not doing the derivation again. I just use the result from our 4.3 or whatever 4.2 exam. And once again, plug in the values. GS is 1 over S plus 1 and GCS is K plus 11S. And that will be your output due to the disturbance. So the complete output due to both signals will be the sum of both outputs. And that is K plus 11S. And that's the expression for Y because of RS and TDS. Now again, our goal is what? Our goal is to select the value of k so that the response to input angle changes is desirable while we maintain minimal error due to disturbance. So this is the output. We have to find the value of k, or we have to choose a value of k such that the disturbance has to be minimized while the response is kept at an acceptable level. This is the output. We can also write down the expression for the error signal, tracking error. You can do it on the next slide once you're done with this slide. Yes. What is what? So this is the output. So in this case, if you go again, go to the description, this output represents, so this is our output. This output represent the actual value of the angle. If you read the last one, the machine operating from both ends of the channel, bore towards the middle to link up accurately in the middle of the channel. Laser guidance system kept the machine precisely aligned. The model of the boring machine control system is shown here. So that's the control system of the boring machine. Ys is the actual angle of the direction of travel of the boring machine, and Rs is the desired angle. The boring machine, when it is traveling and they want to link it up in the middle of the ocean or middle of the both countries, they have to be precisely aligned when you're creating that tunnel. So basically they use the laser guidance system, and the boring machine is basically boring, doing the boring, removing all the, making a tunnel or whatever. And that laser guidance system is keeping it aligned as they don't go right or left from one side and the other side. So Ys is the actual angle at which the boring is happening. And Rs is the desired angle, whatever the desired angle. And you want the minimum, you basically want the zero error between the desired angle and the actual angle, but there will be some error and you want to minimize that error basically. So that's the control. That's the block diagram of the control system that is controlling the boring machine. So the expression of y that we wrote, this expression represent the actual angle, expression for the actual angle in which the boring is happening because of Rs, that is the desired angle, and because of the load that is there on the boring machine, which is represented as the disturbance on the boring machine. Well, my equal sign is going all the way up. Now, if we write down the expression for the error signal between the input and the output, let's do that as well because we have to minimize the error. Es is the difference between the actual angle, the desired angle minus the actual angle. Okay, so you have sorry. Let's keep this. So we don't have a single transfer function. So instead of writing this, we're just gonna plug in the complete expression for Ys here. Rs minus Ys, and Ys expression is k plus 11s, so k plus 11s over s square plus 12s plus k. times RS minus 1 over S square plus 12S plus K times TDS. So the error signal due to both inputs is going to come out to be S square. So right now, S square plus 12S plus K minus K plus 11. 12S plus K minus K minus 11S over S square plus 12S plus K times RS minus 1 over S square plus 12S plus K times TDS. K cancel out, 12S minus 11 is just 1, S square plus S over. And that's the tracking error expression because of both the input and the disturbance. So we can. Yes, go ahead, please. So I have two terms of RS minus that term times RS, right? So I'm combining those two terms. So my common denominator is S square plus 12S plus K. So I'm going to multiply that by RS and then subtract K plus 11 RS. So RS is common, that's why I kept it outside. I'm just simplifying the first two terms. Yeah, basically RS is a common factor out, and then it's going to become 1 minus K plus 11S over S square plus, yeah. So, and then I simplified that. For what? For my, you mean error? Uh-huh. So error is the difference between the input and the output. Yeah. Oh, why is, so let's go and see. I think we got both positive signs. So we have positive sign here and positive sign here. So you're subtracting YS, and that's why this becomes, yeah, both of them became negative. Basically, this became negative and this became negative. Yeah. So sensitivity, again, you are going to find based upon what input you are using, because there is no one transfer function for this, remember, because you have two inputs. For transfer function, you need to have a single input because it's the output over that input to determine the transfer function. So if you're finding the sensitivity, you need to have a transfer function for a specific input. So you can find sensitivity because of RS, first define the transfer function, or sensitivity because of TDS, but not for the whole expression. Yeah. Yes. Back to previous slide. So yes, the value of K, as you can see, you have both K over here and K over here. And remember, S is the frequency. Don't forget about that. Now, if K is large, then of course, this whole gain is going to become small. And if you keep K large, then the denominator is going to be large as well as numerator is going to be large as well. So yes, keeping the K large, and again, if denominator and numerator both are large, your value is not going to be that large for RS. But if you keep K to be large value, then yes, the effect of TDS is going to be smaller on the error as compared to if you keep the K value to be small. That is true. And that's what we are going to look at. We're going to take different k values and plot the error and plot the output to see what value of k works good for the system. But yeah, when you look at the expression, that's what you see. Since k is in the denominator of TDS, we need to have a large value of the amplifier gain, or what was that k, the process gain, in order to reduce the effect of the load on the boring machine. So okay, let me delete this slide. So now we have two expressions, y output and the error. So I went ahead, and again, this is from the book. They took two values in the book for k. They took 100 large value and 20, which is a smaller value, and then they looked at how these two values are affecting the output as well as the gain if your input is a unit step and your disturbance is also a unit step. So this will give us some idea as what value of k may be more suitable for the system to suppress the disturbance signal. So to evaluate yt for a unit step input, we take rt to be ut. We'll take the disturbance signal to be 0. First, we're going to evaluate for rt, and then we're going to evaluate for td. And to evaluate for a unit step disturbance signal, we will take input signal to be 0. So first, we take the value of k to be 100, higher value, and we take disturbance to be 0, and find out what is y only because of your input signal yt. And after you perform the partial fraction decomposition and all those things, and it came out to be this expression right here: 1 plus 1.1792 e to the power negative 60 cosine 8t minus 148 degrees. So as you can see, the steady state value is 1. Therefore, the error is going to be 0. The steady state error is going to be 0 for the value of k to be 100 in this case. That's what we are taking, k is equal to 100. And when we take k is equal to 100 and keep rs 0 and find the expression for td, assuming td is a unit step function, then the yt came out to be 0.01, and then this expression, the whole thing. So the steady state value of yt is 0.01 if we keep k is equal to 100. And we went ahead and plot both output for the input unit step and output for the unit step disturbance. And then we plotted both of them on the same plot. And as we can see, the disturbance signal is quite small as compared to the output signal for the value of k to be 100. So 100 seems to be working so far. Let's look at, observe that the unit response due to the disturbance signal is very small, almost negligible as compared to the response for the value of k to be 100. Now let's take the value of k to be 20 and do the same thing. K is equal to 20, TDS is equal to 0. This will be the expression. K is equal to 20, RS is equal to 0. This will be the expression. And then I went ahead and I used, instead of going through the whole thing, I use two built-in function in MATLAB, TF, which is the transfer function, and I'm going to show you that, and a step that plots the step response. It does not give you the equation, of course, but you can plot the step response directly from your transfer function using the step command. I'll show you that, and it's given in the next chapter when we discuss the next chapter. So I don't have to go and then write down the expression if I just want to plot the step response. If you have to show the expression, then of course you will need to go through the process of partial fraction decomposition and all those things. So I went ahead and used these two, and output response, if k is equal to 20 for a step input, and the response for the disturbance for a step input. Plotted both of them in the same window. The disturbance signal is a little larger signal, as we were expecting, because k value is smaller. Observe that the disturbance signal is still negligible, but the overshoot in the output response due to the unit step input is smaller than the one with k is equal to 100. So that's another thing. If we compare both, this overshoot means a lot in the systems, because overshoot means that your instantaneous value is going very high at some time. So for k is equal to 100, our instantaneous value at some point becomes too large, 1.2. 1.2 or 12? No, 1.2. Disturbance signal is still quite small. And eventually, of course, the output is a steady state, gets to 1. And when we kept k is equal to 20, disturbance is still small, not as small as the other one, 0.01 versus 0.05 approximately. No, yeah, 0.05 approximately. But what happened is our overshoot has reduced a lot. The steady state value is still 1, but the overshoot has reduced a lot. So it's a trade-off. What do you want? Do you want the disturbance, the output due to disturbance, to be extremely small, or you can live with a little higher disturbance output, but you want to reduce the maximum overshoot value? Because again, maximum overshoot value sometimes can harm the system, because you're having a spike which is longer than that you may be expecting in a system. That spike, of course, is momentarily, but it can disrupt the system. So again, you have to, as an engineer, you have to think about the trade-off. Can you live with 0.05 disturbance output for the disturbance, or 0.01 is the one that you're looking for in that case? And if you want the higher peak overshoot, or you want to live with 0.05 steady state output due to disturbance, and your peak overshoot is quite small, the steady state value is the same for both, 1 for the output due to RS, but the peak overshoot has been reduced a lot for this case. So again, as a design engineer, you have to decide what do you want to do. You want to have the peak overshoot and reduce the disturbance, or you don't want to have the peak overshoot and live with that disturbance. Yes. Yeah, so overshoot, basically, remember, that's the output. So it is, if it is a mechanical arm, or it's the angle, but it's not a mechanical arm, it's the angle, right? So the angle is deviating before getting into line, basically. So the overshoot is going to be, it is deviating a lot at that time before it becomes a steady state, and error becomes 0 between the desired angle and the output. Because when output becomes 1 and the input is 1, the error becomes 0. But before it becomes 1, it is moving a lot if the overshoot is very high. And if the overshoot is not high, it just goes and then becomes kind of smooth towards, like in what happened in this part. It didn't rise much, and then it settles down to 1. Then your angle is not really moving a lot. The laser guidance system that you're using, that angle, boring machine angle, is not moving a lot. And in your case, you're saying boring machine, of course, using some arm or something, or some drill to make the bore. So in that case, yeah, you have to keep it pretty constant. You don't want to move it a lot. So perhaps k is equal to 20 value may work better. So just by looking at the transfer function, as we were discussing earlier, if you say we want to make the value of k to be large, yes, disturbance is going to be reduced, but again, the effect of that large value on the actual transient response of the output may matter, as well as how smooth of a transient response you want before it settles down to a steady state value. Okay, so let's see. Let me go back. This is a big problem, so I forgot what we have to do. Steady state error due to a unit step function, sensitivity of the system. Let me see. So this we did. All right, so let's look at the steady state error due to the input. Unit step input. Okay, so let's look at that. So we have the steady state equation that we wrote down. Where is it? Right here. So this is our steady state equation. And let's look at the steady state error value. We can see that the steady state error value, you don't really have to do anything over here. We can see that the steady state value for a unit step function is going to be what? It's going to be 0. Let's do it here. E steady state when EDS is equal to 0 implies limit S tends to 0, S ES only due to RS is equal to S square plus S over S square plus 12S plus K times 1 over S. And when you apply S is equal to 0 in the numerator, both are going to become 0. So the steady state error due to the input is going to be 0 for a step input, and that what of course we can see that that the output is 1. Therefore, there is no difference between the input and the output for both of them. The output eventually becomes 1. So the input was 1 and the output steady state is also 1. So steady state error is 0. That's the second part, steady state error due to a unit step input. Sensitivity of the system to a change in the process GS. So again, GS is the Boring machine, 1 over S, S plus 1. So let's look at the sensitivity if you're changing the process. Sensitivity of the system with respect to G. Transfer function, of course, is GCS over, and again, we're keeping TDS to be equal to 0. And we already did that. Our final result, let's do it one more time. So it's going to be the numerator, so that's going to be GC times the denominator 1 plus GCG minus the derivative of the denominator, which will still be GC times the numerator GC times G. And we know that sensitivity function after canceling and whatever is going to come out to be 1 over 1 plus GCG. After we simplify it and all those, we did that already. So when we plug in the expression, GC is K plus 11S and 1 over S plus 1. So S plus 1 S square plus S over S square plus 12s plus. That's the expression for the sensitivity of the transfer function with the changes in the process. And the process depends, of course. We have the well, K is the gain, the gain in the controller, not in the process, but it is there.